So, how you guys doing today?
Good.
Good, perfect. So it's Friday, right?
Yes, sir.
All right. So let's do the review again. So I started the review session from Wednesday. So I'm gonna have a review again today, and also the other one on Monday. So we can be fully ready for the exam that starts from this coming Wednesday, right? Wednesday, Friday. So, all right. So there's another one you can try. So if you want to make 472 milliliter of 0.045 molar concentrated HCl from 0.212 molar HCl stock solution. And the question is, if you want to make this much of this concentrated HCl solution from stock solution, which is a bit more highly concentrated, how much of that will be needed? From the stock solution. So it means you're actually going to do dilution here. Okay? So you're going to dilute the stock solution to make this concentrated solution in this much. Okay? So I'll give you about 2 or 3 minutes. It's not really erasable. I don't know why. But yeah. Okay. But 2 minutes. Yeah. Maybe you can do milliliter. Yeah. Because eventually you're gonna use what? M1, B1. M2, B2, right? So maybe keep the same unit for volume, it will be much easier, right? So yeah, definitely use milliliter. It's a very good question. I'll never do that to you. To not additional unit coverage of volume. That'll be a lot of work. Okay. Okay, about 1 minute. We'll do this together. Okay, 30 seconds. Okay, so here's the thing. So we're gonna do M1, B1 equal to M2 and B2 over here. So M stands for the molarity, so it's the concentration. And the B stands for volume. Okay, so we're gonna use those ones. We're gonna plug those numbers in, and we're gonna solve for the X. Okay, so we're gonna solve for how much stock solution you need to have. Okay, so I'm gonna put this concentration here. This is concentration, right? So M1 will be 0.212 molarity, moles per liter. And this is what we're solving for, how much stock should we need to have this diluted solution here. So I'm going to put this as X. Okay? And then this will be in a milliliter. Okay? So I'm not going to change this one. So we can keep the same unit on the other side with this one. Okay? So same thing, I'll do the same thing for on the other side. Because the other should be this one, right? So we know the concentration here, which is 0.0545 molar concentrated, times the volume, which is 472 milliliter. Okay, here. So only thing you really have to do is to solve for X. You just need to put this one on the other side. So this is initially what? Multiplication. So I'm gonna put this one on the other side and will become what? Divide by. Okay, so we 0.212 over here. Okay, so as you can see, the unit for the concentration molarity will be cancelled. So solely you can get the numbers in milliliter, which is your answer right there. Okay, so if you do 0.045 times 472 over 0.212. You probably get 100.188 milliliter. So that's the answer. Okay. So technically, what we're doing is try to transfer 100 milliliters of this stock solution in a beaker, and fill the rest of the 472 mils of water. Then you can make this concentration. Okay. Does it make sense? Yeah.
And that's called like dilution.
Dilution, yes, that's dilution. So usually stock solution is very highly concentrated. So you can only transfer a small volume of that stock solution and fill the rest with the water. So you can have a diluted solution, which whatever the concentration you want to make. So we call that actually working concentration stock solution, because this is something you're gonna use for. This is what you just for the storage. Okay. But technically, you just need to do like M1, B1, M2, B2. Just fill all the numbers in. You just put the X for what you're solving for, and there you your answer right there. Okay. Make sense, right? Okay, perfect. Okay. All right, so let's move on to the next one. I think we need some water to clean. Anyway, so the next one. Oh, okay. So if you have this one, okay, if you have phosphate anion, I want you to find out the oxidation number for phosphorus right here. Okay, in phosphate. Okay, and formal charge is -3. Okay. And one thing I want you to remember is oxidation number for oxygen is -2. Okay, so use those numbers for finding out what might be the oxidation number for phosphorus in your phosphate. Okay, this one. Okay, about 1 or 2 minutes. Okay, it's not that complicated. And I will tell you the several rules you might want to know for solving this type of problem. So we'll do this together in 1 minute. Okay, 30 seconds. All right, so here's the thing. So the first rule is that if you have some compounds that has nothing on the right top corner, means it's neutral. So there's just the implied number, which is 0. So we don't show it here. So it means it's a neutral. Okay, it's neutral, right? It's not positive or negative charge in the whole. So that means the oxidation number for these two, whatever the numbers of elements inside, has to be sum in 0. Okay. But here the problem is the oxidation number sum from the phosphorus and the full oxygen should be -3. That's what it means. Okay. So it means I already told you each oxygen will take -2 as oxidation number, but there are 4. So 4 times -2 makes in total -8. Okay, but we don't know the oxidation number for phosphorus yet, so I'm gonna put the X there. Okay? But like I said, the sum of all the elements in the compound has to be same as a formal charge, which is a -3. Okay, so you have a -3 on the right side, but you know this will have full oxygen will have a -2, so it'll be -8. So the X has to be +5. Okay, so in that way we can find out. So oxidation number for phosphorus and phosphate has to be 5. So you can have a formal charge -3 in sum of oxidation. Make sense, right? Okay, perfect. Okay, let's do one more. Okay, have a magnesium chloride. Okay. And I want you to find out the oxidation number for magnesium here. And this chlorine is a halogen, right? So it has a -1 as its oxidation number. Okay, there's just no charge there, so it's 0. Okay, so one might be the oxidation number for magnesium here. Okay, maybe 1 minute. This is quite simple, I think, right? So the charge is 0 there. Each chlorine has -1, and this one is what we're solving for. in some it has to be 0, which is neutral. Right? Okay, so it's quite simple, right? What's the number here? Would be positive perfect. Because the chlorine has -1, but there are 2, but in some has to be 0. So -2, 0, so x has to be 2, minus 2 would be 0. Perfect. This is another one. But the chromium over here, okay? So once again, each oxygen is -2. Oops. And the formal charge is -2 in whole, and this is what we're solving for. Okay? The chromium, this is what we're solving for oxidation number. Okay, chromium. Okay, about 1 or 2 minutes. Okay, 30 seconds. Okay, so we'll be plus 6 perfect, right? So this is 4, but -2. 4 times -2 is -8, but it has to be sum in -2. So x has to be 6, so 6 minus 8 is negative. Perfect. So we're pretty good. Just one more I want to tell you is the hydrogen. Okay, let's do this one real quick. So this is almost same, but now for hydrogen, just remember this as you did for the oxygen, -2. Hydrogen is always +1. There's some exception I'm going to tell you soon, but most of the time, hydrogen is always +1 as an oxidation number, and you're solving for this one. Okay, and as you know, there's no formal charge at 0. Okay. So one might be the oxidation number for sulfur then, because each hydrogen has +1 as its oxidation number. In some has to be 0 because there's no charge there. One might be the oxidation number for sulfur. That's the question. Okay. So if you do this one, +2, 0, so it'll be -2. Perfect. There you go. That's it. It's pretty simple, right? Hydrogen is always +1, but there's only one exception I want you to remember. The hydrogen is always +1, but when it bonds to the metal, like sodium, okay? Sodium hydride here. Sodium is an alkali metal. So if you're in the group 1, the first column in the periodic table, this is alkali metal. Alkali metal always +1. Always +1. Okay? Always +1. But this is neutral, right? So it doesn't matter if it's +1, it will be 2, but it's a 0 here, right? So it means when hydrogen comes as next to the metal as a hydride, in that case it's -1. So now it's neutral for sure. There's no charge there, right? So when hydrogen bonds to the metal should be the one carrying the positive charge, because the metal tends to lose electron all the time. In that case, hydrogen is relatively negative. That's why this is exception. Okay. So if I put this sodium hydride here, you have to put the -1 for hydrogen. But most of the time, hydrogen bond to the other will be +1. Okay. Make sense, right? Okay. All right. So we have some unknown concentration of HCl. Okay. So we're gonna do titration. Okay. And we did the titration so we tried to find out how many moles of HCl in the solutions, unknown solution. Okay? So we don't know the concentration of the HCl yet. So this is why we want to use counter ions, which is some basic compound like the sodium hydroxide. So we used the sodium hydroxide. It was 0.15 molar concentrated, and we had about 57.8 milliliters. Okay? And now you titrate this unknown solution using this one, and then it has the equivalence point. Okay, and then you can find out what was the modes of the HCl in the unknown solution initially. Okay? So this is one. You tied it with this much, and now this is the time you saw that it's passing through the equivalence point and pH change. And what was the initial moles of HCl in unknown solution? Okay? I'll give you about 2 minutes. This is not, I don't think it's very difficult, but if you know the trick, I'll tell you the trick. But yeah. So about 2 minutes. Okay, about 1 minute. Okay, so here's the thing. The titration simply means you want to quantify numbers of your unknown sample by using counter ions. So here we're using some acidic solution here, which is HCl. Using basic solution to titrating that unknown solution there. So technically you're using what? Hydrogen cation from HCl. You're using hydroxide anion from NaOH. That's the very basic solution over there. So think about it. 1 proton is from 1 HCl, because there's only 1 hydrogen in 1 HCl. And 1 hydroxide anion will come from the what? 1 sodium hydroxide. So numbers of proton from here and numbers of the hydroxide anion should be the same numbers of what? Is sodium hydroxide and HCl. So you can consider them as like the same numbers of moles of each. Makes sense, right? Because 1, 1. So we're actually going to do neutralization, right? So we're putting this one to make it water. So when you get to the neutralization point, your pH level will reach at 7, which is we're going to see the equivalence point. That means at pH 7, in this two mixture, you have the same numbers of H plus, same numbers of OH minus. That is also same as numbers of HCl and numbers of OH minus, because it's a 1, 1, 1, 1 ratio. Make sense, right? Okay? So meaning when this one added to your unknown solution, it reach at the equivalence point means same numbers HCl, same numbers NaOH is there. Okay? So what you really need to do is to find out how many numbers of moles of NaOH added to there, which will be the same numbers of moles of HCl were there initially. Because it's a 1 to 1. 1 to 1. Okay? So let's do that. So to find out the moles of what? NaOH, whenever you have a concentration, molarity, 1.5, this is the same as what? Moles per liter. Okay? So molarity is the same as moles per liter. How many moles of something you have in 1 liter of solution? That's what it means. So this is the same as the molarity here. The problem is your volume is a milliliter. Okay? So you have to multiply that by volume, 57.8 milliliter. But the unit doesn't match up for the volume, so you need to do unit conversion for this one. So 1,000 milliliter is equal to 1 liter. Okay, so you have this one to be in liter. You have to do 57.8 over 100 mil, and put the new unit there, which is a liter. So this unit will cancel, so you can get 0.0578 liter. Okay, over there. So then, now you can put that number here. And liter, so now it adds up on the unit because it's the same now. So this is moles per liter. This is the 0.0578 liter. The liter will cancel top and bottom. So you get a numbers in moles. Okay, I believe that is 0.00867, I think, yeah. And then this number of moles is what? Same as NaOH and or OH minus. So this is the numbers of moles of NaOH. And then once again, at equally balanced point, you can also assume the same number of moles HCl is still there too. That is the answer actually. Because it's equivalence point. We're assuming the numbers of the contour ions should be same as the what we're solving for. That is what we can find equivalence point. Okay? This is what we call the equivalence point. It's equal for each. Makes sense, right?
What is this? What are the numbers of the answer?
This one.
Mm-hmm.
It's the same. Yeah. So
Can
you
read it
had.
out loud?
Hmm?
Can you read it out loud?
Oh yeah. Oh sorry. So 0.00867. Yeah. But simply you just need to do this one for me. That would be fine. It's 0.15 times 0.0578. Yeah. And that's. Makes sense, right? Can you guys do just one more? Okay, just do one more and move on. So same here, same problem here. You have an unknown HCl solution, so you don't know how many moles of HCl in there. But I titrated with the 0.20 molar concentration with about 200 milliliter, okay? So one might be the moles of HCl initially in the unknown solution, okay? So basically what you really need to do, solve for this one. Because there should be also same numbers of HCl anyway, at equal balance point, okay? Okay, so what's the answer? It would be 0.04, perfect, moles of HCl there and also NaOH there. So what I just did is the same. So concentration times volume will give you numbers of moles, but the problem is this is 200 milliliters. So I'm gonna switch this one to the liter, which will become 0.200 molarity with moles per liter, same thing. And also 0.20 liter, because I do the convert the unit for the volume to liter, so it'll be not 200 milliliter, 0.2 liters, so that can be canceled, the same unit there. So you have a 0.04 moles of what? NaOH. Also same numbers of OH minus. Also same numbers of H plus, or same numbers of HCl, because it's a 1:1:1:1 ratio. So that is also the answer too. Makes sense, right? Okay, perfect. All right, let's move on. Okay, so next one. Okay, so here's the thing: when heat is released from the system, what might be the enthalpy change for the reaction? Okay. It's minus the negative or positive. So there's a couple of things I want to tell you. So whenever you have a system, okay, you have a system. So system means a very small portion of the space. So maybe it could be a small chemical reaction in the container, or some very sealed glass bottle or anything. So a very small portion where you're gonna have a chemical reaction, okay? Chemical reactions there. And then everything else in the universe is the surrounding, okay? So everything else. So if you do sum of system plus surrounding, it's equal to universe, because it's literally everything. Okay? So system is small thing, the everything else is surrounding. So when heat energy is going out from the system, meaning the system is losing heat energy, right? Because they're releasing the heat energy to outside, meaning they're losing energy, right? So in that case, enthalpy change of this chemical reaction will be negative because they're losing the heat energy. So this is the point of the system. For system, they're losing energy because they're releasing heat to outside. Makes sense, right? So we call this exothermic reaction. Because it means it's going out. So it's exo means what? It's going out. Okay. So if you have heat energy is being absorbed into the system, so heat energy maybe is going in instead of going out, then now this chemical reaction, by doing this chemical reaction, they're getting energy from outside. So it's actually going to be what? Positive. Okay. So when heat energy is going into the system, it will be positive. We call this endothermic reaction. Okay. Endothermic reaction. So heat energy is going into there. That's why it has a positive sign, because the system will gain energy from outside. Okay? There's a couple more things I want you to remember. The one more thing is the Gibbs free energy. Okay? So Gibbs free energy simply means will actually tell you how spontaneous your system or your reaction will be. So if you have a Gibbs free energy change is negative, meaning your reaction will be spontaneous. Spontaneous. So it means whenever you have a chemical reaction that has a negative sign, negative number for the Gibbs free energy change, your chemical reaction will happen automatically. Even though you do not put any energy into the system, you didn't force the chemical reaction go forward, they just do it for themselves. Okay? So that means it's a spontaneous reaction when it's negative. Okay? When it's positive, it means it's non-spontaneous. So non-spontaneous means either you're gonna do something to the system, they will not do anything. So either you're gonna heat it up, meaning what? You're gonna put a lot of heat energy into the system, or you're gonna do some physical pressure or anything. Unless you do something to, usually energy input into the system, they're not gonna do the reactions. Unless they have a really good enough energy coming from the outside, so they can have enough energy to overcome the activation energy. So for Gibbs free energy change, if that is negative, means it's spontaneous. If it's positive, it's non-spontaneous. So this will happen automatically, voluntarily. This one is not. Okay, unless you have enough energy or input into the system. Okay, so this is also something I want you to remember. Make sense, right? Okay. All right. Okay, so. Okay, here's the multiple choice 2. What is the definition of energy? Okay, so energy simply is a capacity to do work. And the work we mean by in chemistry or science, meaning you're moving something that is matter. So that has also what? Matter has a mass, right? So something that has certain mass to other position. So for example, you have a chalk right here, right? It's right here, and I move this one to this position. To do that, this is the work that I just showed you. This is work. It's moving to other place right here. And to do this work, I need to have energy to do so. Okay? So if this is fixed on the floor, so I don't have enough energy to just move it, means there's no work that has been done because this has not been moved. Okay? So this is what we mean by energy. This is something that makes you be able to do work, which is moving something that has mass to other position. or make something go faster, moving faster. If it's already moving. Can I move on? Okay. All right. The next one. Okay. So which one is the least kinetic energy? Okay. Oh, sorry. So here's some choice. The first one is electrical energy. Electrical energy. The second is thermal energy. This is the same as the heat energy. The third one is chemical energy. And the last one is the light energy. Okay. And try to find the least kinetic energy. So the kinetic energy means this is energy that generated from motion of matter. So something is moving, so by it's moving, so it creates some kinetic energy. So if we have something that is moving really high speed, means you can say, oh, that is very high in kinetic energy. The other one is potential energy. So this is kind of opposite. So potential energy means it's just the matter has the amount of energy is potentially stored in the system. So if you think about like a ball is rolling down up and downhill, obviously the ball like coming down from the high position, they're going to have a higher kinetic energy, meaning their potential energy as position, right, will be lower. So they're using their potential energy into what? Kinetic energy, by using the energy by doing the motion. Okay, but always the sum will be, these two will be the same. Okay. Anyway, so yeah. So in here, the least kinetic energy is chemical energy. Okay. So the electrical energy is, as you know, is created by motion of what? Electrons. Thermal energy is the way you can transfer the kinetic energy into the space by radiation. So think about it. If you have only two ways to deliver the energy, which is conduction and convection, if you think of the universe is almost what? Vacuum, right? But we still get the sunlight. We can have a really good amount of heat energy onto the earth, because most of the heat energy from sun, it actually transforms into the light energy. So it actually transforms and with a certain amount of the heat energy. So heat energy and the light energy can be very good example of kinetic energy, because they actually travel through the space and travel through the medium, which is like conduction. So these two will be good example of kinetic. But the chemical energy is kind of a potential energy, because the compound usually have a chemical bond. So to break the chemical bond, you need to have energy. Okay, that means when they form the chemical bond, they release the energy, usually in form of a heat. Okay, so this is the amount of the energy already stored in the compound, and then they can use it for some other biochemical energy or the chemical heat energy when they do some chemical reaction. So this is not been used by doing any motion yet, but potentially in the chemical reaction can be used like there. So still, this is a good example of potential energy, because it hasn't been used for making anything move yet. Okay, does it make sense? Okay, just do you like this question? Okay. All right. So this is a good example. It's like maybe this one you have this one has this ball on the very high position here. This should be very high in potential energy, but almost zero kinetic energy. Okay, and then there's one more thing I want you to remember, the internal energy of system, which could be once again very small thing, if it matter, small container or small bottle or anything, should be always the sum of kinetic energy plus potential energy. This is always the same. Okay? Either they're gonna lower the kinetic energy to higher the potential energy or the other way. It is always working in this way here. Okay? Either they're gonna have a lot of energy in form of a kinetic or potential. The sum of the initial original amount of the energy stored inside in the system will be always the same, but just up and down on those two. Okay. I'll move on, but yeah, this is the kind of thing. All right, let's do. Oh, okay. Time goes really fast. So the next one. Oh, here, this is a really good one too. So if you have a 150 grams of water, okay, and initially at the 20 Celsius degree, which is the room temperature. Usually 20 Celsius is room temperature. So this room should be at 20 Celsius degree right now too. Anyway, so when I hit this water up to 77 Celsius degree, okay? So you wanna heat up the water, this much of water there, and then the question is how much heat energy do you require to do so? Okay, so Q stands for the heat energy. Okay, so Q is always in joule, which is unit for the energy because it's heat energy. Okay, and you want to find out if you have a 50 grams of the water at room temperature, you want to heat up the water up to 77 Celsius degree. How much heat energy required there? That's the question. Okay. Okay, so I'm actually gonna tell you. So this is kind of a I don't know if you guys remember this one. Okay, so this is the heat energy in joule. This is the specific heat. Okay, specific heat, and this is the mass of the matter, and this is the change in temperature. Okay, so this is in gram. This is in the Celsius. Okay, and this is in the joule per Celsius and grams. Okay, so specific heat is like this one. How much heat energy is required to increase the temperature of something by 1 degree, if it's 1 gram. So if you have a 1 gram of water, okay, if you have a 1 gram of water, maybe it's a 20 Celsius degree, but you want to heat up 1 gram of water by 1 degree, so maybe at 21 Celsius degree, right, at the end, then you need to have a 4.18 joule amount of energy. That's a specific heat. So specific heat means what might be the specific amount of the energy is required to heat up the something that is 1 gram by 1 degree its temperature. Makes sense, right? So that is why if you do the specific heat times mass by change in temperature, will tell you how much energy you need. Because obviously, if you need this much of energy by increasing 1 degree, how about you have a 2 grams? You have to multiply this one by 2. And how about you want to increase the not just 1 degree, but 2 degree? You also need to multiply that by 2, right? So if you want to get the energy amount of the heating the water by 2 grams by 2 degree, you have to multiply this one by 2 and another 2. So multiply this one by 4, this is this, that. Right? So technically what you really need to do is this number will be given. You don't have to memorize. So that was a 4.18 joule per Celsius grams times. So the mass was what? 150 grams. So I'm going to switch to 150 grams. And the change in temperature is always the final temperature minus the initial temperature. Final temperature minus the initial temperature. So final temperature is 77. This is what you're looking for. So it's 77. And the initial temperature is 20. So 20. Okay? So if you do this one, the 77 minus 20 is 57. Okay? And then if you multiply 4.18 times 150 times 57, that is your answer right there. Okay? So can you guys do this for me? Okay, so 4.18 times 150 times 57. Okay, that would be 35,739. Perfect. Perfect. Okay, there. That's the answer. Okay. We don't have time, but I will just stop here. But I promise you, we'll have another review on Monday too. So we'll finish up the review, and then if you have any